Good afternoon, good morning, good evening, whenever in the world you are. I'm Douglas Nagy. I'm Engineer Emeritus from Liburdi Turbine Services, and I'd like to welcome you to another one of our occasional webinars here on LinkedIn Live. Today's topic is Liburdi Powder Metallurgy, and I'd like to introduce our speaker, Justin Kuipers. He's an accomplished materials engineer with 16 years of experience in the gas turbine industry. He's been with Liburdi Engineering for that amount of time, I should say. During his career, he's been lead investigator in hundreds of cases, including failure analysis, life cycle prediction of gas turbine components. Justin has been active in research in the development of repair processes and rejuvenation, heat treatment of superalloys with a focus on single crystal alloys, as well as wide gap repair technologies. He's also just come back from Turbo Expo in Boston, where he did a bang-up presentation on some advanced inspection techniques for single crystal blades. So welcome, Justin, and we look forward to your presentation today.
All right, thank you, Doug. So as advertised, this is the introduction to LPM, which stands for Liburdi Powder Metallurgy. You can see my contact information on the screen with my email address there, jkuipers@liburdi.com. So to begin, just to introduce the Liburdi group of companies, I fall under the umbrella of Liburdi Turbine Services, which provides hot section component repairs. But within the Liburdi group of companies, we also have Liburdi Automation and Dimetrics, which offer automated welding equipment solutions. And we also have Liburdi Engineering, which offers failure analysis, as well as mechanical and metallurgical consulting services for the turbine industry. So as mentioned, LPM falls under the umbrella of Liburdi Turbine Services. Liburdi Turbine Services is a leading provider of advanced component repairs aimed at extending the life of hot section components. And we service components from each of aircraft engines, aeroderivative light industrial engines, as well as heavy duty industrial gas turbines. All right, so moving on to LPM. What is LPM? It is a modified wide gap brazing repair process that was developed and patented by Liburdi Turbine Services. LTS has an over 30-year track record with LPM and have repaired thousands of component sets using the repair technology. We've used it extensively on industrial components, both heavy-duty industrial and aeroderivative components. And it's also an FAA-approved process that's used for aircraft component repairs. What are the advantages of LPM in comparison to other repair technologies? So in comparison to welding, which is a commonly used repair technique for turbine components, LPM offers both improved strength over commonly used weld fillers, and it also eliminates or significantly reduces the cracking or distortion that occurs with welding. And so with welding, those are issues that are commonly encountered. And so that limits the size and the surface area that we can repair on components. Whereas with brazing and LPM specifically, it's a process that allows us to repair much larger surface areas, much larger crack sizes and defect sizes, because it avoids the cracking and distortion associated with welding. In comparison to other wide gap brazing processes, the big advantage of LPM is that it allows us to do much larger gap sizes, so up to 10 times larger gap sizes. Material restoration is possible with LPM, up to a ½ inch gap size, whereas with conventional wide gap braze repairs, they're generally limited to between 4 and 40 thousandths of an inch. And we see at the bottom of the screen an example of a part that has had LPM applied to it and repaired. So those are kind of the purple stripes you see on the part there. And then we see that same part that's gone through another full service interval, and we see the repair materials held up well during service and is free of cracking, even in the areas that had cracked during the prior service and required repair. So getting a little bit into the technical side of how the process works and why it offers these advantages over other repair processes. As mentioned, LPM is a modified wide gap brazing repair process. A braze is an alloy that has a lower melting temperature than the material it is being used to join or repair. So in contrast to welding, when we're welding, we're melting both the repair filler material as well as locally melting the part itself where the repair material is being applied. With brazing, we're only going to a temperature where the filler material or the braze alloy melts, but the part itself that is being applied to does not melt. For nickel and cobalt alloys, brazes are typically composed of nickel or cobalt alloys. They contain generally chromium and may contain other alloying elements, but in particular, there's generally boron and or silicon that are added to these alloys in order to lower the melting point. So as previously stated, we need an alloy that has a lower melting point. The way that's achieved in nickel and cobalt alloys is by adding boron or silicon, which are termed melting point depressants. So the addition of these elements is useful in that it allows us to create braze alloys with lower melting points, but they also are detrimental, and so we want to only add as little of these melting point depressants as possible. So how do we achieve this? The way that this is achieved is that instead of mixing our high melt and low melt constituents together, LPM consists of two layers. Um, just want to say for Doug and Jeff, I can see those comments popping on the screen, and it's a little bit distracting if we can wait until have that discussion after. So with our LPM process, we have a part that comes out of service and we have damage on our component. So we see an example at the left center of our slide here. We've got an example of a crack or some damage on the surface of a component. With our LPM process, we go in and mechanically remove that damage. So we'll use tools or machining to remove the damage. And then, as stated, we apply our LPM materials as shown at the second from the left in the center. So the LPM materials can be applied in two forms, either a putty or a tape. The putty is generally used for where we have irregular shapes, such as cracks, or example, we've removed a crack and we have a groove, and then we can use our putty to fill that groove that's been created. Or in contrast, where we want to do uniform buildups of thickness on a wall, we can use tapes. Our first layer is the high melt constituent, which has a composition and melting point similar to the part that's being repaired. We then apply the braze constituent on top of that in a fixed ratio. The part then goes through a heat treatment, and after going through a heat treatment, we end up with solid metal where our repair materials were applied, and then we machine or blend the part back to the original contour. Looking at a more microscopic level of what's happening during the heat treatment process, we see at the bottom an example of what's happening with our powder particles. So we start with our high melt filler powder particles packed into our groove. We then go through, as we increase in temperature during our vacuum furnace heat treatment, we start getting ligaments or sintering happening between our high melt powder particles. We then heat treat to a temperature where our braze has melted, but the part and the high melt powder have not melted. And at this point, when our braze becomes liquid, it then flows into the spaces between our high melt powder particles and fills those voids between our high melt powder particles by capillary forces. We then go to an even higher temperature where we get consolidation and homogenization of our repair joint, and we get solid grains forming upon cooling. So we see here some examples of what the microstructure under optical microscopy looks like of our LPM repair material. We see at top right micrograph at higher magnification where we've got our boride phases and also some characteristic microporosity that exists. So that's expected and typical of the process, and that's accounted for in our repair joint mechanical properties that we have for our LPM material. At top center, we see an example of the LPM that's been bonded to a MARM 247 casting. So we see good bonding, no unbond, no defects at our interface between the LPM and our parent material. And you see an example that we have some fairly thick buildups that are repairing through-going defects in the wall of a MARM 247 part. We're going to move on now to some examples of repairs that we do with our LPM process. Starting with repair of the PW2000 stage 3 vane. This is an FAA approved repair that we do. The parts experience hot corrosion damage during service, which you see at top left in the seal slots on the sides of the components. We go in and we mechanically remove all of that corrosion scale and damaged material and end up with a widened slot or groove. We then fill that whole slot and build up material on that side face with our LPM materials. You see at top center an example of a part that's had the LPM putty applied on that surface and has gone through the vacuum furnace heat treatment and been consolidated. And then we go through and do final machining and restore the geometry of the slot on the side of that component. And then it's ready after coating to go back into service again. We see at bottom an example of the microstructure in that slot. So we see at the bottom of the micrographs are MARM 247 base material. And then on top of that, we see the LPM material that's well bonded and has a dense microstructure to that part. And here we see the same component type after it's gone through a full service life. And so we see that the LPM material is held up extremely well in service, that it's got the same dimensions and shape as it had going in. And when we did a cut up, we see our LPM material is free of damage and looks effectively like it did prior to going into service. Here we have another example of a stationary seal segment component. These components regularly experience significant damage during service. You see at top left the photo of a part where the honeycomb's been burnt up, the conical surfaces are badly oxidized, and the part has been distorted during service. So we then go in, machine away all of that damaged material, open up the seal slots on the side of the component as well, and build up all of those gas pass surfaces and seal slots with our LPM material. At the top right, you see an example of the component after it's gone through the vacuum furnace heat treatment and had the LPM consolidated to the part. And so we've applied LPM tapes on the flat conical surfaces at top and bottom, and then we build up that knife edge feature with our LPM putty material. Then you see at bottom right, the component after it's then been machined back to its nominal dimensions. The honeycombs are reapplied and the part is recoated, and it's a fully serviceable part, which then goes back into service. And we see at bottom left, number 4, an example of that same LPM repaired part, which has gone through a full service interval and comes out looking in pretty good shape, held up well during service, and then would be ready again as needed to go for additional LPM repair cycles. And so we've done 3, in some cases, maybe 4 repairs of the same components using this process and significantly extended the life of these components that get badly damaged during service. Here's another example of an extensive LPM repair where we're doing extensive reconstruction of the geometry of an HPT vane. So you can see at top left examples of the damage that occurs during service. We've got burning, cracking at the leading edge and trailing edge of the component. you see missing material, and in particular, the oxidation of those leading edge shower head cooling holes is extremely difficult to repair. And so we go in, again, remove all of the damaged material and apply our LPM materials. You can see the putty in the green state that's been applied at the top right. And so that part would then go into our vacuum furnace heat treatment. And then we see at bottom left an example after it's been through the vacuum furnace heat treatment. We've got our consolidated solid LPM deposit material on the part where it had been applied. And then naturally, we've plugged up the holes that previously existed on the component. So we then have to go in and remachine using EDM the location and at the right angle of all of those holes. And you can see an example of a part that's been LPM repaired and then had the geometry and cooling features restored and then been coated and is ready to go back into service at the bottom right. Another application of LPM is that we can use it for wall thickening and or throat correction of nozzle guide vanes. So the throat area of nozzle guide vanes will increase over extended service due to thinning and bowing of the airfoils. This open throat results in loss of power and efficiency, which can be significant. And so that's one thing that often needs to be considered doing repair of vanes. One way we can use LPM is to apply material to these surfaces. As shown, we apply our tape material to these surfaces to build up the thickness of those walls. And then the parts are heat treated, we consolidate them, and we get a thicker wall that comes out, and then the parts can be machined in order to restore that original throat area of the components and restore that efficiency that's been lost. We're going to touch a little bit on the mechanical properties of LPM. We've done fairly extensive testing of the properties at different temperatures. Here's some examples of tensile strength of our LPM repair material. When we do the testing, for the most part, the tests have consisted of creating butt joints, as you see at the bottom of the slide. So we create generally most of the data we've created has been for 1/4 inch. We see examples also of 400 thousandths of an inch gaps in the table above as well. And then we subject it to the testing. We've also done some testing of pure LPM material as well, which tends to fall generally in line with our butt joint test data. To put the numbers in context that you see there, this tensile strength is well in excess of common weld filler alloys such as IN 625, but somewhat below than conventional nickel-based superalloy casting materials like MARM 247 or IN 738. Looking again at the creep properties or the stress rupture life of LPM, this is a Larson-Miller curve. So the further towards the top right of this graph that the curve falls, the stronger the material. So we see conventional weld alloy like IN 625 at the bottom of this curve, and we see that our LPM well exceeds the creep properties of IN 625, but again is somewhat lower than conventional superalloy castings like IN 738 or MARM 247. And in terms of creep strength, the LPM material essentially is more or less in line with the creep strength of commonly used cobalt alloys like X40 or FSX 414. But in fact, we've seen that parts like shown at the beginning where we have cracking in a cobalt alloy with the original design, we'll repair those cracks with LPM and the part will come back out of service without cracks in the LPM where it had cracked originally. And even in some cases, it will have cracked beside the LPM in the cobalt alloy because the load has been shed to the weaker alloy. So we can say that LPM exceeds the properties of conventionally used cobalt-based superalloys. One other thing to note with LPM is that it can be customized. So because of the way the process is applied, we can use different high melt and low melt powders. And in doing so, we can come up with solutions that are custom to the application. Some examples include that we've done cubic boronitride, as well as alumina as hard-facing materials or abrasive tips. And we've also done chrome carbide versions of LPM, which you see a micrograph at the bottom left, as a hard-facing material. There's other applications that can be done as well. So for example, particular brazes can be used if oxidation resistance is the property that's most critical to the application being applied. Or if we need higher strength versions, different filler materials can be substituted. That concludes my presentation. I thank everybody for tuning in and for your attention, and I want to open the floor to any questions. So the first question I've got here is, if the part's already been repaired by LPM, is it possible to weld repair on LPM area? Yes, it is possible, but it is also difficult. So we have done it, and you have to, it's helpful to be aware that there's LPM or brazed materials there, and there's particular considerations. It's probably more limited in how extensive of a weld can be applied. It can be done, but it is more challenging and probably more prone to cracking than the original casting would be. Next question says, you mentioned microporosity. Is that allowed, or do you eliminate it using hot isostatic pressing? That's a good question. Yes, microporosity is allowed. I mean, even in castings, there's a certain amount of casting porosity that exists. We have a characteristic amount of microporosity, and so when we characterize the deposits, there's a certain amount that we expect and accept. We do have a specification for what that is, and so we examine that, particularly when we're doing first article type development of repair processes using LPM. We'll look at that microporosity. Is it possible to hip? The challenge with hipping braze alloys is that you get entrapped gases because your braze material tends to remelt during the hip process, and so we have looked at whether or not you can do hip at lower temperatures. So there's kind of a trade-off between going to a temperature where you can actually collapse the voids and not going to a temperature where you're remelting your braze. For the most part, that trade-off isn't worth it, and we can live with the microporosity, but there is an avenue for eliminating it using hip, but it's not trivial. What about the TBC coatings that is needed on these types of turbine parts? How you process influence the coatability? No, you can TBC coat. Really, we do all types of coatings over our LPM material. So we have extensively applied aluminide coatings and thermal spray coatings over our LPM material. And there's really, particularly with overlay coatings like M Crawleys and TBCs, there's really no limitation whatsoever. And in fact, that's an important part of the process, is applying those coatings back onto the parts, just as critical as the repair with LPM or weld itself is the reapplication of those coatings. And so it wouldn't really be viable to have a repair process that can't be recoated over. And so, yes, there's no limitations with coating on LPM. And do you thermal spray coating in-house? Yes, we do. Absolutely.
Okay, can I just recycle back to one question? Ahmad did ask about repairing LPM. Can it be welded? And you did mention that it's weldable with care and caution.
Mm-hmm.
But you also showed an interesting slide of a heat shield that was LPM repaired, and then after service could be LPM repaired again. So I guess that begs the question, is if you did a repair with LPM, why would you want to weld? Just re-repair with LPM. I get the impression that re-repairing with LPM is quite viable.
Absolutely, yeah. Yeah, there's no limitation on re-repairing a component that with LPM that had been previously repaired with LPM. Yeah.
Okay, thank you. All right, is there any other questions out there? We're happy to hear them. You also can see some email and phone numbers scrolling at the bottom of the screen if you jot those down. And due to administrative error, probably mine, we don't have Justin's in there. If you contact either Jeff or myself, we'll be certainly able to connect you up to Justin to get the real answer. Okay, well, if there's no more questions, we're at the end of our half-hour slot. So I want to thank Justin for his presentation on LPM. I want to thank our viewers, especially for tuning in and taking time out of their busy days to see what we're doing and what we're up to. And hopefully they find that there's something useful in LPM, maybe for a repair or a process that that you're interested in, and we'd be happy to hear about it. So thank you very much, folks, and hope to see you next time when we do another one of these LinkedIn Lives. We're getting a little better at it. Not perfect, but we're getting there. Thank you so much, Justin.
Yeah, thank you.